Module 3.2 will investigate the cumulative distribution function and the inverse cumulative distribution function of the standard normal distribution. These two functions are widely used throughout finance, and we will explore this. We'll take this opportunity to also introduce machine error. And so the goal here is simply to explore methods to compute the standard normal cumulative distribution function and its inverse, and to identify and illustrate machine error. Machine errors stems from the fact that real numbers are not stored precisely in computers, and they are rounded, and depending on how many calculations are involved, and it will govern how much machine error plays a role. If you're new to finance, and perhaps you don't know this function, but most people are familiar with the cumulative distribution function of the standard normal. The standard normal is basically a normally distributed variable with mean 0 and standard deviation 1. The cumulative distribution function is the integral over the probability density function, which is inside the integrand of this integral. And basically the CDF is simply the integral from minus infinity to some value d of the PDF of the standard normal. And so we need a function that solves for this value. And for example, the Black-Scholes-Merton uses this function twice, one for ND1 and one for ND2. And so unfortunately, there's no known analytic solution to this particular function, and thus we have to approximate it, and hence having access to a computer is helpful. And there's many available approximations, but generally it's numerically computed. So the percentage point range is from minus infinity to plus infinity, not inclusive. The range of the cumulative distribution function is 0 to 1 inclusive. And so the probability density function is the familiar bell-shaped curve. The goal is to figure out how much accumulated area there has been up to some value d. And so the cumulative distribution function runs from 0 to plus 1. The function typically looks something like this, where you can think of these as standard deviations. So plus or minus 5 standard deviations is going to capture the vast majority of the CDF. There are many approximation methods. The one that I've used for many years comes out of a book called Stewart and Ord's Advanced Theory of Statistics. And this is a very accurate estimation method. D has to be greater than 0. And so if I have a negative number, I can simply do 1 minus the absolute value of that negative number. And so this is a summation sign from 0 to 12 of a fairly complex function, but very easy to write a computer program that will do that. As we'll see when we look at the code, that there is machine error if we if we start out with the value of d, we estimate nd, and once we have the value of the CDF in d, we can compute the inverse CDF to get the implied d back. And what we observe here is this is not absolute 0. However, the errors are very small. This is plus or minus e to the minus 15. If we do the same sort of analysis in the cumulative distribution function, these errors again are extremely small. And so the conclusion is that machine error is de minimis when it comes to estimating ND or the inverse ND. And so in summary, this particular module explores different methods for computing the standard normal cumulative distribution function and its inverse. And we basically just simply introduced this idea and illustrated machine error. And we turn now to examine the R code that is used in this particular module. Module 3.2, when you unzip the file that's made available, what you'll discover is it's a very simple single piece of R code if you double click on the RPROJ file, it launches this program. And in this particular case, I left these values here from a prior run just to show you directly what happens when I take out the trash. This environment is cleared out. If I ran this several times without this particular clearing of the trash, so let me go ahead and run these packages, and then if I just run this code, it generates some plots. And so there's 1 plot, 2 plots, 3 plots, 4 plots. So there's 4 plots here. If you'll notice, if I ran the code again, there's 1, 2, 3, 4, 5, 6, 7, 8. So if you ran this multiple times when you're debugging and you're trying to find some error, you're going to end up with a whole bunch of plots here. And so that is why when we clear out the environment is line 6. If we clear the console, all this material down here, that goes away. And then we can clear out the plots by running that line. And all that does is it just really helps to keep the RStudio environment clean when we're trying to find mistakes and errors. And so the way this particular program works, we'll take number of observations, say 1,000, have some mean and standard deviation. Because we're focused on the CDF and inverse CDF, we can generate random numbers and then compute the CDF and PDF and do all kinds of different calculations on these standard variables. And so line 23 simply generates 1,000 draws from a standard normal distribution. The quantile value is 0. Then the accumulated CDF is a half. The PDF value is 0.3989423. And we can see if there's any difference in the values that we estimated. And so to generate some plots, what we'll do is we'll store a number of observations. In this case is 201. We'll create a set of vectors that holds different values of n and d, depending on how they're estimated. We'd start out with a mean 0, standard deviation 1. What this loop does is it loops over the 201 observations. It loops from minus 5.0 d value to basically plus 5.0, and it increments by a small increment so that we get values all the way across the CDF. And so we'll calculate the value of d. With that value, we can compute the if we had something other than mean 0, standard deviation 1, we could incorporate that fact. In this case, the standard deviation is 1, estimated mean is 0, so line 50 doesn't do anything, doesn't change the number. ND1 is one way to estimate it is with P norm, and then if I wanted to estimate the PDF, I could use D norm. If you happen not to remember what this is, you can just copy it over here to the help file, take a look at it, and it basically lets you know that D norm gives the density, and P norm gives the distribution function, and so on. And so basically, I start out with the value of D, I estimate ND, and then with that value of ND, I estimate a new value of D. And that provides a measure of sample error from the true value of D to the value of D1, which has gone through the translation to calculate ND1 and back to the inverse of ND1. And then we repeat this exercise, except for now we look at the value of ND1, compute the value of D. With that value of D, we calculate another value of ND, and then look at the machine error there. And so when we run this loop, and again, these programs are run very fast, the Q norm might produce nans every now and then. I don't think that causes a problem. And then we can look at the maximum error in both cases. And what we observe is the maximum error in the case of n is a number e to the minus 16, whereas the maximum error d is e to the minus 11. Both of those are extremely small, and so it's not a concern. Plotting is very, one of the nice things about R is it's very easy to produce plots of a variety of different forms, and you can get as sophisticated as you wish, but this is just a simple plot of the value of the PDF. And so this is the standard normal density function, and I would encourage you to spend a little time getting familiar with how this plot works. An alternative plot that you could do is the CDF, and then we could look at the estimated error, which is we looked at before in the PowerPoint presentation, and then finally we could consider the error related to the cumulative distribution function. Again, this is a very simple program. There's not a lot here. In today's environment where you have pre-packaged functions, it's very easy to do these calculations. But again, we're trying to learn R at the same time coming up the learning curve of being a good quantitative financial analyst.